All right. Hello, everyone. Good morning, good evening, wherever that you are. I'm Hamid Boigeri from the University of Nebraska Lincoln. Welcome to the session on software security number 4. We have 6 presentations for today, and each will have 5 minutes. After all the presentations, then we have time for questions and discussion. It will be about half an hour. The first paper is default mutual information-based crash triage for massive crashes, but I'm not sure whether any of the authors are here or not. If we cannot find them, then we can start with the second one, and when they join, then we can actually have that presentation. So how about starting with the second paper? So the second paper is Out of Sight, Out of Mind, How Vulnerable Dependencies Affect Open Source Projects by Levin Khin-Shar. Levin, are you around? Levin, can you hear me? I think your microphone is off. You are muted. It seems that he has some technical issues. Let's start with the next one, and then we can get back. So I got some. Gyeonggi, are you here? Can you hear me? Sorry for the technical issues. I understand that it seems that there are some connection issues. Hello again. Can you hear me now?
Yeah, I think we can hear you. Yep.
Perfect. Thank you. And Gyeonggi, are you here or not? I know that you said that there are some connection issues. So any of the authors from the first paper, default? If not, we can start with the second paper because Levin just told me that he is around. So Levin, are you available and are you ready? Okay, sure. Please let's start. We cannot see you. Your video is not on. Okay, let's go to the third paper. Andreas, I believe that you are around, right? Can you hear me?
Yes.
Perfect. So let's start with the third paper, identifying challenges for OSS vulnerability scanners, study and test suite.
Yeah. Hi. Okay, in the next 5 minutes, I want to explain why you cannot trust your vulnerability scanner to detect known or all known vulnerabilities, at least in your Java components. So, hi, I am Andreas, and this is joint work with Henrik and Serena from SAP, Ben from University of Dortmund, and Eric from the University of Paderborn. So the recent Log4Shell vulnerability has once more shown that the use of vulnerable open source packages is a known issue. Suddenly, developers were faced to detect the known and vulnerable Log4j jar in all kinds of different forms and all platforms. They had to detect it in Docker containers, on virtual machines, on server environments. They had to detect it in different jar files. They have to detect it in so-called fat jar files and packaged within Lambda environments. So we asked ourselves, what are typical forms that developers use to include open source packages within their application and in their project? And we also ask ourselves, how do state-of-the-art vulnerability scanners actually perform when trying to detect known vulnerabilities on those different kinds of forms? And to give an answer to this question, we first conducted a case study on more than 7,000 projects developed at SAP using the dependency scanners Eclipse Steady, Dependency Check, and a commercial scanner. For all scanners or for all projects, we generated the bill of material and then manually investigated how developers actually include open source packages. To give an answer to the second question, we actually computed for a set of free and commercial dependency scanners the F1 measure, so how these scanners perform on open source packages in these different forms. So what kind of forms did we identify? We identified 5 different forms. So developers usually include open source packages directly and as an unmodified jar from Maven Central. But what we also often saw were so-called patched jar files. So developers forked an open source project, then did some slight adaptations, and to indicate these adaptations, they changed the name of the open source artifact a bit. What we also commonly saw were so-called fat jars. Developers bundled multiple jar files and open source packages within to a single so-called fat jar file that bundles all these different packages. In this case, the original names of the artifact files of the open source artifacts were still present. A special case that we found were so-called bar fat jars. Like fat jar, they bundle multiple packages, but the original artifact names were lost or erased. And another special case that we commonly found were repackaged fat jars. In this case, the fully qualified names of the classes were actually changed to avoid name clashes. So how do these scanners perform? So as I already said, we computed the F1 measure on a set of different open source packages, applied the modifications, so produced the different forms of these open source packages, and then checked the performance of different dependency scanners. And what we see that even in the easiest, so the unmodified case, all scanners yield results, but their performance heavily varies. What we saw for patched and fetch jars, so when the original names of the artifacts were only slightly changed or still reconstructible, we found that most scanners still yield results. Also, their performance most oftenly decreased. And the most interesting insights we had was in the case of bar and repackaged fetchers. So when the original artifact name was changed or the fully qualified name of the classes actually changed, then most scanners did not yield any results, or their performance was really worse. So we found if the artifact names or class file name changed, most tools actually fail. And this indicates that these dependency scanners rely more on the names of the artifacts and the classes, but do not actually check what code a jar file actually contains to identify a known vulnerability within a jar file. So to come to a conclusion why we cannot trust our vulnerability scanners, our study showed that all tools fail to cope with all these forms, although they are quite common, at least in the Java world. And we saw that name changes in the artifact names heavily decrease their performance. Another insight is the CVE is typically reported only for one specific package. This package occurs on public repositories like Maven Central in all different kinds of forms and is also included there in all these different kinds of forms. Thus, one single vulnerability reported for one specific package usually affects many downstream public open source projects as well. Yes, thanks for your attention. I'm happy to answer your question later.
Okay, so let's get back. Thank you, Andre, for your nice presentation. Sorry, it seems that I was muted. So we have time for question, answer, and discussions after all the presentations. For now, let's get back to the first paper, default mutual information-based for massive crashes, presented by Jiangyi Chen. Jiangyi, can you hear me?
Hi, yes. Yeah, I can hear you.
Yes, please.
Okay. So, hi, okay. Hi guys, this is Zhong Yi. I'm from National University of Defense Technology. This work is called Default Mutual Information-Based Crash Triage for Massive Crashes. I'm going to talk about the high level idea of this work. So fuzzing is very powerful now. As of February 2021, the fuzzing infrastructure has found many bugs in Google's products, and in those open source projects. So crash triage is needed. This includes 2 steps: crash deduplication and fault localization. This process is imprecise, time-consuming, and labor-intensive, which is a very heavy burden for analysts. So here is the workflow of crash triage. In step 1, we cluster the many crashes. Then the crashes in the cluster would share the same root cause. In step 2, we select a unique or a representative crash from each cluster. In step 3, we locate the fault at certain basic blocks. Those basic blocks, we call them root cause basic blocks. But there are some challenges. For crash deduplication, accuracy and efficiency sounds contradictory. For accuracy, the best solution is to use fault localization techniques. To achieve efficiency, we don't want to involve any heavy techniques like those fault localization techniques. For fault localization, the challenge is that existing approaches cannot be used to capture the long dependency among those root cause basic blocks. Luckily, we have 2 insights. The first insight is we quantify the crash relevance of basic blocks using mutual information. And the second insight is that we recover the sequence information of basic blocks using neural networks. We use neural networks to identify the root cause basic blocks and capture the long dependency among them. So in crash deduplication, basic blocks with the largest mutual information, we call them criterion basic blocks. They're used as the criterions of grouping and the selection of representative traces. In fault localization, the basic blocks with less mutual information are removed to shorten the long crashing traces. So with the shortened crashing traces, the neural network can this can be sent to the neural network, and the network can capture the long dependency of those root cause basic blocks. The system looks like this. So first of all, the fuzzing infrastructure produced many crashes, and those crashes were sent to the first module, crash deduplication module, and this module outputs a set of unique crashes. In this set, the root cause are unique. So then for each crashing trace in this set, we send the crashing trace to the second module, fault localization module, and this fault localization module outputs a set of root cause basic blocks. So we believe those are the root cause for the crashing trace. So for the first part, crash deduplication, this step 1 is to do grouping. Okay. First of all, in the first round, we calculate the mutual information of basic blocks. The basic block with the largest mutual information, we call them criterion basic blocks. And if there are some crashing traces that contain this criteria basic block, we group them as group 1. So for the rest, we do another round of calculation. And for the second largest For the basic block is the second largest community information. We group them as group 2, and so on and so forth.
Just 30 more seconds.
After that, we select the representative trace from each group. So what is the representative trace? Before that, let me introduce what is a non-representative trace. It is the trace that contains the criterion basic block B bar and another basic block B1, which is the root cause of another unique crash. So this trace is not clean and cannot be used for fault localization. So what is a representative one? A representative trace contains the criterion basic blocks B bar without other root cause basic blocks of other unique crashes. So the second module is to locate the fault. For the dataset construction, we use AFL-FAST to mutate the crashing trace. This would produce many non-crashing inputs, and we can mutate those non-crashing inputs to produce the traces that include a portion of basic blocks that are also included in crashing traces, but are irrelevant to the crash. The purpose of this step is to make sure that statistic characteristics of the produced traces are significantly different from that of the original crashing traces. Then we filter out the irrelevant functions, and we do another round of filtering to filter out irrelevant basic blocks. Then the traces are shortened and can be used for training the network. So the input of the network is the sequence of basic blocks, the shortened traces. And we use one hot vector encoding. The length of the input is the length of the longest trace, and we pad the short inputs with stereo vectors. The output of the neural network is 1 or 0, meaning that it triggers the crash or not. The network structure is very classic. We use the classic LSTM using attention mechanism. Okay, and we evaluated.
Sorry, we don't have enough time, so the time is already. So can we actually conclude your presentation and then go to the next one?
Okay, so we evaluated this tool, and it turns out that this tool is the false positive and the false negative rates are much less than other tools, and the performance is also good, especially for the crash deduplication. The processing time per program is 19 seconds, and each program contains about 1,110 crashing traces. Yeah, that's all. Thank you.
Very interesting work. So we have some question and answer at the end of all the presentations, and we have some more time over there, hopefully. So let's go to the next paper. Out of sight, out of mind, how vulnerable dependencies affect open source projects. And I hope that, yes, please go ahead.
Yeah. So earlier I have a connection issue. Sorry about that. Okay, now I'm ready.
You can start sharing your screen and we are ready.
I just share the screen, but guys, okay. Can you see the screen?
Yes.
All right. Hi, everyone. My name is Shah. I'm going to talk about our January 1st paper called Out of Sight, Out of Mind, How Vulnerable Dependencies Affect Open Source Projects. Open source libraries are commonly used in software projects nowadays, and turns out that they also often contain security vulnerabilities. And as the usage of libraries grows and libraries being dependent on several other libraries, security analysis tasks of those libraries become very complex. And what makes it worse is that there's a report from Kulai et al. In 2018. It says that developers often do not review the security of third-party libraries that they use. So as a result, dependency vulnerabilities, that is vulnerabilities in directly used libraries and transitive libraries, could be missed. So this led us to analyze the prevalence, types, severity, persistence of dependency vulnerabilities in software projects, along with the relationship between project attributes like popularity, complexity, size, and dependency vulnerability counts. So we want to answer questions like, what are the security risks library users should be aware of with respect to the use of dependencies? And is it sufficient for a library to just fix the vulnerabilities and release the new version as soon as possible? And how effectively can we reduce security risks in software projects with respect to the use of dependencies? So to answer those questions, we took a RIPA dataset from Munaria et al., which is published in 2017 in MC, which contains about 1 million software projects in GitHub repository. Among them, we randomly sampled 450 actively maintained projects written in 3 popular programming languages, Java, Python, and Ruby. And we checked out each commit made between 2017 and 2018 for the 1-year period, and perform a full security scan using a commercial software composition analysis tool called ViraCode. So basically, this tool support many languages, including those popular languages that we are analyzing here. It will generate the software dependency graph of a given project and analyze the graph to identify direct and transitive libraries used. And it will report CVE vulnerabilities in those libraries, as well as vulnerabilities that are not listed in a CVE. So we want to answer 2 main research questions. What are the prevalence and common types of dependency vulnerabilities in open source software projects, and how persistent are they? And what are the relationships between vulnerabilities in the dependencies with the attributes of the project and its commits? So here are some important, or at least interesting, results and findings. First of all, how prevalent are dependency vulnerabilities? Well, the short answer is quite common. So if you look at this table here, for example, Java projects, the percentage of dependencies with vulnerabilities is up to 12.3% on average. Likewise, for Python, 7.8, and Ruby is 5.3. And also, we found that denial of service and information disclosure are common across the 3 languages that we studied. So it means development of practices and tools to combat these 2 types of vulnerability could be is needed. And also, another interesting aspect that we looked at is some security-aware developers. They do diligently monitor CVE updates and patch vulnerabilities that are reported in CVE. The thing is that we also find that the percentage of non-CVE vulnerabilities, meaning the vulnerabilities that are not yet published in the public database yet, is also pretty high, especially for Java and Ruby projects. For example, for Ruby, it's up to 41.5% on average across the 150 projects that we analyzed. So it actually means that developer could still miss some of the vulnerabilities in their project dependencies, even if they actively monitor the CVE updates. We also look at what percentage of vulnerable library is not updated to non-vulnerable version, even though there is availability of the patch. Well, interestingly, we find that there are quite a few cases where the dependencies that are vulnerable are not updated, even though there is a fix available. For example, for Ruby project, 36.7% on average of the vulnerable dependencies were not updated, even though there is a patch available, so which is quite alarming. And last but not least, we also look at the correlation between project attributes, several project attributes, and dependency vulnerability counts, so that we can measure how could we reduce the security risk. So it turns out that most of the attributes, like popularity, size, and things like number of developers, doesn't really matter. What matter is, could be quite trivial, but interestingly, it depends on the direct and transitive dependencies that is used in a project. So it means that managing dependency could be more effective at reducing security risk rather than increasing more developers or managing the project size. Well, with that, let me stop here, and I will be looking forward to the Q&A session. Thank you very much.
Nice study and nice talk. So we have some questions for you, but then let's actually finish all the presentations and we get back to questions. So the next
Thank you.
talk, sure. So the next talk is Practical Automated Detection of Malicious NPM Packages by Adriana Sechvia.
Can you hear me?
We can hear you.
Okay, cool. And I'm assuming you can see my screen.
We can, yes.
Okay. Hi, everyone. So my name is Adriana, and today I will be talking to you about our paper entitled Practical Automated Detection of Malicious NPM Packages, a joint project with Max Schaefer from GitHub. For those of you who were unable to listen to our 20-minute presentation, this is the too long didn't listen version. So a key term in our project is NPM. NPM is a JavaScript package manager that contains a registry where JavaScript packages are uploaded and updated. And NPM is a very widely used package registry given the popularity of programming languages like JavaScript and TypeScript. In fact, in any given day, around 20,000 NPM packages release updates in NPM. And as with any large system where third-party code is stored and served to users, security is a concern for NPM as well. However, most of these updates are your run-of-the-mill benign package updates. Some, not so much so. Like, for instance, this package, MongoDB, which tried to impersonate MongoDB, which is a very popular package in NPM, and tried to steal users' information. Other packages behave like Jasmine, which became compromised, meaning an attacker took over the code, published malicious code to also steal users' information. So with this picture, the problem for NPM becomes how to find these malicious packages in an ocean of benign ones in a way that doesn't burden the NPM engineers by having to further manually analyze packages. An observation we had when considering previous research, as well as our own analysis of malicious packages, is that they exhibit certain patterns that are repeated throughout many packages. Such patterns include making use of certain libraries or using APIs that encode information that these malicious packages want to steal, for instance. And a potential solution when trying to automatically find patterns is a machine learning-based solution, which is exactly what we went with. A machine learning-based solution necessitates data, features, and a learning algorithm. NPM helped us with our data, giving us a data set of malicious and benign packages, which we refer to as our basic corpus. And even though in this data set, the malicious packages are oversampled, because we wanted to detect these types of packages, this was okay for our initial purposes. In our features, we try to look for certain APIs and code that would enable a package to conduct malicious behavior, a list of which you can see on this slide. But specifically, we try to encode characteristics a package has. More importantly, though, we try to see how do these characteristics change during a package's lifetime. So our intuition is that by focusing on the change, we can capture sudden behavioral differences in cases when packages are compromised, like the package Jasmine I showed before. So the imbalanced data set I mentioned earlier conditioned the choice of our algorithm. In the end, we used decision trees, naive Bayes algorithms, and one-class SVMs, all of which have been used in past scenarios with imbalanced data sets successfully. Using these three machine learning ingredients, as well as further pre-processing and post-processing mechanisms, we built our approach, full details of which you can find both in our paper and the longer presentation. For now, I will focus on whether our approach works, the evaluation. We specifically wanted to check if our approach can be accurate, robust, and quick. We evaluated our approach in these three contexts, but for this version of the presentation, I'll focus on the robustness. So in this evaluation context, we wanted to see if our approach would work in a realistic scenario and be able to reduce or help the NPM engineers with the manual work they have to do afterwards. So for this evaluation, we conducted a sort of sliding window experiment for an entire week, where for each day, we would train our classifiers, predict the status of packages uploaded that day, and then manually triage the predictions. And then we would continue the next day with the difference that we would retrain our classifiers adding the triage predictions of all the days before to our training set. So we continued the same experiment for 5 more days. For the full results of this experiment, please refer to our paper, but the highlights were that we found 95 new malicious packages, which were all taken down by NPM after we reported them. In addition, we found out that the rate of false positives was quite low, especially in the later days of the experiment, where the ratio of malicious packages to benign packages gets lower and more reflective of the actual rate of malicious packages in NPM, meaning that there wouldn't be much manual work for NPM engineers. So to conclude, today I spoke to you about the problem of finding malicious packages in NPM being one of detecting highly unlikely events, but very harmful events. Our intuition was that a machine learning-based solution that deals with imbalanced data set would be useful in this case. And our evaluation showed that that was indeed the case and that such a solution can help NPM engineers. I look forward to talking to you all and reading your questions, but if any one of you has offline questions, I'm leaving my email address here. Thank you so much for listening to my presentation.
Excellent. Nice work and really interesting actually talk. So let's go to the next one. And definitely we have question and answer, hopefully about 15 minutes at the end actually on the presentation. Actually paper is exploiting input sanitization for regular expression denial of service. It's by F. Borders.
Hi everyone, can you hear us? Are we muted right now?
We can hear you.
We can see your slides.
Okay, all right, great.
Okay. Hello everyone. My name is Xin, and I'm from the Purdue EC department. Today, me and Alpha are going to talk about exploiting input sanitization for regex denial of service. So, what is regex denial of service? Regex stands for regular expression, and it matches a set of strings. And this matching process is conducted by another component called a regex engine. And the problem comes here. Some regex engines can have superlinear time complexity, such as the orange and the brown line shown here, given certain regexes. And we call those regexes vulnerable, because if this computation happens on the server side, it could steal computational resources from legitimate clients, and thus causing a regex denial of service. Previous research has shown that 10% of regexes in NPM and PIP are vulnerable, and that there are a lot of vulnerabilities in the top 1 million websites. However, those readout studies assume having some knowledge about the server implementation, and we wonder if we can study readouts with weaker threat model. So what black box approach did we use in the study? For a client-server model, both client and server side would often have sanitization, which includes regexes. And our first approach is based on the assumption that server-side sanitization repeats client-side. And here's one example from Mozilla. Because we are interested in server-side regex, we start with client-side, and we do that by parsing front-end HTML and JavaScript code. And for the second approach, we search for the API specs that web services publish online, and those specs often contain regexes as well. So to conduct readout study in a black box manner, the study is divided into 3 steps. First, we use the 2 approaches to find a list of regexes. Second, we used off-the-shelf tool to find those regexes that are vulnerable. And third, we probe the web services which use those vulnerable regexes, and we analyze the response time and status code to find readout vulnerabilities. And now is the finding.
Thank you, Xin. So starting off with our data set, for HTML forms, we have randomly sampled 1,000 websites of Tranco 1 million. And for APIs, we have collected all of the documents on apis.guru, which is an online API specification directory. With this data set, we first find the proportion of web services using at least one regex. We found that regexes are frequently used in client-side sanitization in both HTML forms and API specifications. We also found that in HTML forms, there was significant regex reuse. We found 5,000 regex uses, but only 33 of them were distinct. But what proportions of these domains use superlinear regexes? We found that superlinear regex use varies by interface type. Out of the domains using regexes, on the API side, 13% use at least one superlinear regex, and on the HTML side, only 2% do so. In total, we found 17 domains which use superlinear regexes. Now we run probing experiments on these domains. We probe each service by following Steico and Pradal's methodology by sending them two types of requests. One type of requests includes strings, which are expected to trigger the superlinear behavior of the regex. We calculate the difference between the response times to see if we produced superlinear behavior on the server side. If we observe the difference, we conclude that there's a RDOS vulnerability. We found 6 domains with RDOS vulnerabilities, including AWS and Microsoft. The vulnerabilities have been patched since. If we did not observe a difference, but we were able to send a valid initial request, we conclude the service either uses a safe engine or a different sanitization scheme as specified from the client side. We found 3 HTML and 1 API domains under this category. And if we couldn't send a valid initial request, then we deemed the probing experiment to be unsuccessful. API specifications expose more RDOS vulnerabilities than HTML forms, and we want to help software engineers move from using an unsafe regex engine to a safe regex engine very easily. So we patch a client and server-side input sanitization library called AJV, which has millions of dependent projects. In our study, we found that over 99% of studied web services were safe from black box RDOS analysis. This is a very small risk, and it should inform how software engineers regard RDOS. On the other hand, Steico and Pradal reported in their 2018 study that their gray box analysis found 12% of websites using Express to be vulnerable. Comparing their results to this study, on the API side, we found 1.3% of services to be vulnerable. And these are our contributions. Thank you for listening, and we are happy to answer any questions in the comment section. Thank you.
Excellent. Really nice work, and I really enjoy your presentation. We definitely have question and answer at the end of actually all the presentations, and we have just one more presentation. The next, hiding critical program components, ambiguous translation, by Qiujun Zhang, please.
Yeah, thank you. Can you hear me?
Yes.
Can you hear my voice and can you see my screen?
We can see your slides, and also we can hear you. And
Okay.
Yes, perfect.
Got it. Okay, let me start. Hello, I'm Qiujun Zhang. I'm going to talk about our paper, Hiding Critical Program Components via Ambiguous Translation. Software system often contains critical program components such as patented program logic. And there are a few techniques that can be leveraged to hide critical program components, such as obfuscation, packing, and encryption. These techniques make the analysis difficult, but it is practically feasible to obtain the critical program components protected by existing techniques. In this presentation, we introduce new desirable properties ambiguity and show our proposed approach Ambiter prevents the adversary from identifying and pinpointing the correct critical program components. For existing techniques for hiding critical program components, first, obfuscators aims to make the original code difficult to analyze, and the dynamic analysis, including first execution techniques, are highly effective in handling these techniques. Packers or cryptors create a program containing compressed original program as data, and uncompresses and executes the original program at runtime. Because a packer-generated program seamlessly unpacks and executes the original code at runtime, dynamic analysis can obtain the original program. Protectors are essentially advanced packers or cryptors equipped with evasive anti-analysis techniques. First execution techniques can handle evasive techniques by forcibly executing branches regardless of the predicate conditions. And we also consider 4 desirable properties of critical program components hiding techniques: evasiveness, complexity, context sensitivity, and ambiguity. And here we introduce ambiguity as a new desirable property. Let me explain this briefly. The program is not ambiguous when an adversary obtains a successfully decoded or decrypted critical program component, and the adversary can certainly say that this critical program component is genuine. In other words, if the adversary cannot determine whether the critical program component is correct or not, we consider the technique has the ambiguity property. Our proposed approach, Ambiter, aims to impose challenges in terms of not only existing street properties, but also ambiguity. Let me explain how Ambiter achieves this property ambiguity. Ambiter leverages the state machine, but it's different from a typical state machine. First, it makes a transition on every input. Unlike the typical state machine, in Ambiter, if an input does not match with any possible transitions from the current state, it makes a transition to the state which has a similar transition condition to the provided input. And second, Ambiter can generate an output without requiring a state machine having a matching transition. It means that when the input is not exactly matched with the transitions input, it applies the difference between the input and the transitions input to the output transition rule. We evaluate the Ambiter in terms of evasiveness, complexity, and the context sensitivity. In this presentation, I will briefly explain about reverse engineering attempts using static analysis and the symbolic execution tools. The result shows Ambiter effectively hides critical program components. I will briefly explain about reverse engineering Ambiter using static analysis tool first. Static analysis tool can be used to analyze Ambiter to identify possible output values that can be generated. A data dependency graph shows that all variables are contributing the value of the result. This is correct, but this is too coarse-grained. It does not provide the particular order of the state machines. That is very important information to find the input for critical program components. And second, also the reverser uses symbolic execution tools to reverse engineer the genuine critical program component translation logic of Ambiter. However, none of the symbolic execution tools we used finished the analysis in a week because of the state explosion. So we additionally conducted 2 experiments to measure the time cost after we enhanced the symbolic execution tools manually. We prepare Ambiter instances with different numbers of transitions and a single transition, but with different input lengths. It takes about 3 hours, 2 days, and 4 weeks to finish the analysis with 4, 5, and 6 transitions respectively. And also they take more than 15 hours, 2.9 days, 13 days to finish the analysis when input lengths are 6, 7, and 8 respectively. This shows that analyzing even a single transition is time-consuming. So we propose ambiguous translator that imposes fundamental challenges to the existing analysis techniques. More details are also in the paper. Thank you.
Much for the presentation, and it's for the discussion and question and answering time. So we have some that already, but I really appreciate first to if others please turn on their video so that we can actually have the discussion. Excellent. And anybody else, please actually join the discussion if you have any questions. So let's start with the questions that Andreas asked from the Lemin. So do you want, Andreas, do you want to actually repeat your questions? Everybody actually be aware of your question.
Yes, for Shah, I have 2 questions on the slides. I saw maybe you said it on slide 11 that you it states about vulnerable instances, did you actually check if a library makes or the project invokes a vulnerable code or is actually vulnerable?
Yeah, I saw the questions. Thank you very much.
Ah.
So we use this Veracode SCA tool, which will basically generate a core graph of software projects, which include the libraries and the transitive libraries and so on. So as long as the a library in one of the powerful graph is stated to have, for example, the denial of service vulnerability listed in CV or non-CV, then we count as one. So so you can say that it is a static analysis base. So we don't actually know whether it is really used in a runtime or not. So
Okay.
so yeah, I agree that some false positive as always with static analysis too. Yeah.
So is it correct that you
Sorry, yes.
that you miss a lot of vulnerabilities in frameworks like Spring, for instance, because they use heavily use reflection or dynamic bytecode writing, or did you cover these cases?
Oh, definitely for reflection cases, we would miss. Yeah, we will miss. It depends on the configuration of the tool as well, I guess. So you can do either under approximation or over approximation. So if you take over approximation, well, we can just include all the libraries as long as we see it in the imported cases. Yeah. So, but we don't want to have so many false positives, so we take an under approximation in this case.
Okay, super cool. And my follow-up question is, did you found any further reasons why developers do not update? So further reasons that Kula did not?
Yeah, there are two things. What I mentioned about Kula, his study say that developers usually do not analyze data. And I can relate to myself from my own experience. I tend to develop software time to time, but I as I'm a security person, I always check my code for sure. I don't want to have my code, being vulnerable and being exposed, especially to my students. But the thing is, I never ever check the libraries until I do this study. Then I realize, oh yeah, that's true. I never update the libraries. Yeah. So one reason, one finding that we have, but which is not reported in this 5-minute presentation, is that one possible reason could be in this, most of the vulnerable libraries, at least for the 150 project that we studied, came from the top, the top 5 vulnerable libraries came from the popular software ecosystem, like from Google, from Apache, including Spring that you mentioned. So maybe that's a reason, like trust, right? Security originates from trust. So when we use a library from Google, we think it's secure somehow, although usually it's not the case. So that could be the reason. And another point is why they do not update, even though the patch is available. Well, we didn't include a user study, but informally we do discuss with those experts from. But it's a usual suspect, like the developers are affecting known existing functionalities and stuff like that. So perhaps take note is perhaps the developer, like the library developer patch. Maybe they also need to do more, like better documentation of how to fix the compatibility issues and so on and not. Yeah.
Okay.
Excellent. Any other questions? So we have 5 more.
Actually, I see another question from Jasmine.
Please go ahead.
Okay, I'll just give a quick answer. Well, I think it's a good point, which I never thought before, to be honest. Well, we just analyzed all the commits. We didn't really distinguish between development only or production only. Something for the future work, I guess.
Yeah, I was wondering actually if you could, because you said you generated the project's call graph. So maybe you could use that to see which ones are used, I don't know, for testing or something like that, if it's in development or not, or if it's even at runtime, it's a bit more difficult, but it may explain why some vulnerable dependencies are not being updated by, developers, because it's development only, or it's not at runtime, then they may care a little less. Than,
I agree with that, yeah.
So it could be interesting.
Yes.
Thank you.
Thank you for the yes, no.
Perfect. Any other questions? So I have a question. The false positive rate of your approach malicious NPM packages is pretty low, especially when compared with the state of the art. Any ideas, any actually that helps to achieve a huge improvement compared to the state of the art?
We were running the sliding window experiment I mentioned during my presentation, in which in the beginning we had an oversampling of malicious packages, basically, which tended to make our classifiers detect find more malicious packages because how the probabilities in the modules worked. But what we did that I haven't really seen before, not sure if other papers have included this, is we then took all of these packages in any given day and manually analyzed the results and then balance our training sets so that the false positive rate, the malicious packages rate reflected the actual rate of malicious packages in NPM, which tended to decrease the false positive rate. On the other hand, this could have also caused us missing certain malicious packages, because we do mention it in the paper. We don't really go through all of the package updates in any given day. Like, we don't manually analyze all of them because that would take too long. We only analyze the ones already flagged by our classifiers. So the false positive rate. So basically, my answer is a two-part answer. First, the rate of malicious packages in the training set, and second, this might come at a cost of missing certain malicious packages.
Thank you. Any other? Yes, please.
A question by Andreas. Thank you for the question. I think in like most of them could be used, especially our observation, to check. So the question is, are the features that you use to identify malicious packages transferable to other languages as well? And the answer is they are, especially the observation that we should look not at individual packages, but how they change. I think that's applicable to other languages as well. There are certain incarnations of our features in this specific version of our approach that are targeted to NPM, JavaScript, and TypeScript. But if we could do a mapping to these other languages of these behaviors we're looking for, then they're definitely transferable.
Oh, okay. Thanks for the answer. And interestingly, did you found a lot of cases of obfuscation? So was this an important factor in identifying, okay, this is malicious, like having parts of the code encrypted, remote code loading, or does it also occur in benign packages?
So in our paper, we talk about using a approximation of whether there is minified code, which is something related to what you were talking about, not exactly that, but like the closest thing to that. And we did find that malicious packages tend to do it much more often than benign packages. So that could be helpful to the models.